way they do, they're driven by these changes in salinity and temperature according to a pressure gradient acceleration. But those currents are also affected by the Coriolis force. So exactly the same as in the atmosphere, you've got a pressure gradient acceleration and inverted commas force, onto which you add Coriolis, because the Earth spins whether you're sitting on top of land or you're sitting on top of the water, or sitting at the bottom of the water. You're still getting a spinning effect. And that balance is exactly the same balance as you get in the atmosphere. We call it the geostrophic balance. And you get the same sort of deflected movement from the original path by about 90 degrees, according to this geostrophic balance between the Coriolis force and the pressure gradient acceleration. Most oceans are in geostrophic, most currents are in geostrophic balance. What does that mean in terms of how the currents behave?
The northern ones turn clockwise and the southern ones.
Yeah, what else? You're a mariner, you've got currents. What do you tend to think? If most of the ocean currents are in balance, what it means is that they're not going to shift, they're not going to suddenly reverse or suddenly change, they're not going to go in a different direction. So again, if you're sailing or you're using the oceans, you can guarantee, at least that the surface currents, assuming there's geostrophic balance, that they will always run in that way from west to east, from north to south, from here to there. The currents don't tend to shift. If you get a change in currents, then you are getting serious changes in the Earth's ocean system as a whole, because there's because you do have this balance. It's less obvious because there's all sorts of other factors that we'll see, but for instance, if you take the Antarctic circumpolar current, that just keeps on going round and round and round and round and round, rather like the Antarctic westerlies. It just goes round and round and round and round. It's in balance. Totally balanced system. The geostrophic, the pressure gradient, the characteristics don't change very much. So Coriolis is the same, pressure gradient is the same, so the current just goes round and round and round. And the same is true for those where there's relatively little change as well, which, so we have down here, there's no land to get in the way and complicate matters. The same is basically true for anything in a big ocean area. As soon as you get close to a land, then you start getting other processes coming in. So what drives the Antarctic circumpolar current is, yeah, there's a wind component, but effectively it's the pressure gradient acceleration Coriolis which determines where it's going. And that isn't going to change over time, particularly much at all. The top of the ocean is affected obviously by what goes on in the atmosphere and by pushing of that atmospheric by the wind itself. And effectively the surface water is pushed about by wind. The wind just pushes and pushes the atmospheric circulation. And it just pushes the surface of the water. We see that over recent weeks whereby effectively there is a pressure difference as well, but strong winds just push that surface water in front of it, just piles up in front of it, acts as a bulldozer, just pushes it over the way. So there is a link between currents and atmospheric circulation. And if the atmospheric circulation changes, that will have an influence on currents. So we know what happens in there, Hadley-Ferrell polar cell. We can see that going forward, and we can see how that drives the currents. So for instance, we know that the north and south Hadley cells are reflected by the equatorial currents, and we can see them being pushed around, especially in the Pacific where they're much clearer. We can see that equatorial countercurrent, because effectively you've got these two cells which is pushing the water in different ways and then pushing it back in the other way. So there is an element, if your salinity and your density is effectively uniform, temperature is uniform, salinity is uniform, then the wind will determine the way it will go or counter the density. The problem with the oceans as well is that we don't just have a big empty earth, we've got land. And as soon as water in the oceans gets close to land, it's deflected by the land, and we get boundary currents which are affected by this link between the ocean and the land. And there are two types of boundary currents, western and eastern. Western boundary currents flow away from the equator, eastern boundary currents flow towards the equator. And this is, the western boundary is the western boundary of the ocean. So you've got to remember it's the ocean's western boundary, the eastern boundary is the eastern boundary of the ocean. So if we look at that, here we get currents coming down towards, so if we go, that's western boundary currents flow away from the account, eastern boundary towards. Here's an eastern, Pacific eastern boundary flowing down here. So here's California. So what sort of water and what impact does that have on California? It's cold. It's very cold. So this wonderful idea of these Californian beaches, you know, with everything going in the water, is very cold because it's coming from the northern Pacific. And what does that lead to, particularly San Francisco?
Fog.
Fog. Wonderful picture in the Times. I know you don't read the Times, but it's a lovely picture of Golden Gate Bridge, you know, with the mists around it. So very cold, foggy current coming down here. It's a boundary current. It's the eastern boundary current going towards, of the eastern Pacific going towards the equator. Eastern boundary current here going towards the equator. Cold water coming up from here. So this is why this is very dry in here. That also is why that's very dry, because this is cold masses, so it's not so easy to get the evaporation getting into the water, into the masses. Cold doesn't produce the amount of precipitation. And then we have the western, so the eastern boundary currents along here, sorry, then the same in here, Benguela current coming up the coast of, I think we talked about this before, what's the deserts around here? The Kalahari Desert, very, very dry, despite the fact it's right next to the ocean. And we get the one coming down off Spain, coming down, not quite so well developed because you've got a much more complicated ocean basin in the North Atlantic than you have in the Pacific. And if you looked at the other ones, going from the equator south, transporting warmer air up, this is what drives this boundary current, which is the origins of the Gulf Stream, the origins of our North Atlantic drift. It's because of that boundary current, with bringing the warmer water from the equator right up here, generating this enormous amount of depressions that we keep getting. It's warm, it's wet, it's moist, produces the origins, and therefore is the main transport of warm water up to high latitudes. Same here off Japan, called the Kuroshio current. Kuroshio. And there are similar ones off here, off northern eastern Australia, and the same is true with the Peru or the Humboldt current coming down, Brazil current rather, Peru and Humboldt this side, Brazil current coming down here, bringing warmer air. This is again the reason why either side of these land masses you get such different water masses. These are boundary currents which are driven by the system. And these lead into these rather important things called gyres. Gyres are circular sort of circulations of water. And each of the big oceans, there are 5 major gyres. Sometimes they are subdivided, sometimes they're seen as bigger. This doesn't mean nothing gets out of them, but effectively we have North Atlantic gyre, South Atlantic gyre, North Pacific, South Pacific, and the Indian Ocean gyre, where circulation is such that effectively you go round and round and trap the water in between. So these are the key large-scale gyres: North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian Ocean. The side effect, as some of you may have seen, is the plastic vortex. Has anybody seen this before? Have you seen the Greenpeace stuff on it? I was going to try and get the link, but it won't do it on here, so I'm going to have to see if it will let me into the internet. It probably won't. So if I go in plastic vortex. Here we are. Basically what happens is that the journey of trashing, here's our circulation, here's the gyres, the North Pacific, South, here's the rubbish coming in, Japan. You can begin to see it being transported around. Gradually gets more and more concentrated until over time you can actually begin to see the concentration, and it's just going to get heavier and heavier in the middle of these gyres. And this is not just a Greenpeace oversimplification, it's actually true if you sort of see where this material goes to. Do you know what the most useful event was in tracking gyres and tracking movement of surface ocean currents over the last sort of 5 to 10 years?
Oil spill?
Sorry?
Oil spill?
Limited. And I'm trying to think which one it was. It was a cargo of plastic. Is it plastic ducks or shoes? Ducks, wasn't it? That went overboard, and they, I mean, quite seriously, you know, oceanographers suddenly realised actually there's fantastic data.